A água é um dos recursos mais valiosos do planeta. No campo, nas cidades e nas florestas, na agricultura, na indústria, na geração de energia e no lazer. Ela é fundamental em todos os momentos das nossas vidas. Mas a água não está sempre disponível na quantidade e na qualidade que precisamos. No Brasil, temos longos períodos de seca, enchentes frequentes e forte demanda pelo uso da água em regiões com pouca oferta. Para enfrentar esses desafios, foi criada a Agência Nacional de Águas, a autoridade do governo federal responsável por monitorar, planejar e regular o acesso e o uso das águas gerenciadas pela União. A ANA estimula a gestão participativa, que envolve o poder público e representantes dos usuários e da comunidade. Afinal, cuidar de um bem precioso como a água é uma missão da ANA e também de todos nós. Saiba mais sobre a ANA no site www.ana.gov.br.
Com apenas 8% da rede bancária na região, o Banco do Nordeste concentra quase 65% do total de financiamentos de crédito de longo e curto prazos em todos os setores da economia. O Banco do Nordeste é também o principal agente financeiro do agronegócio em sua área de atuação, respondendo por 54% do crédito rural na região. Atuando para promover o crescimento sustentável na região Nordeste, por meio de apoio financeiro às atividades agropecuárias, o Banco do Nordeste oferece linhas de financiamento com as melhores condições de mercado em diversas atividades, seja para custeio pecuário, custeio agrícola, máquinas e equipamentos, investimento, comercialização e exportação, agricultura irrigada, energias renováveis e armazenagem. O FNE, principal fonte de recursos do Banco do Nordeste, possui as menores taxas de juros do país, prazos diferenciados e bônus para pagamentos realizados em dia. Tudo isso aliado às melhores soluções, com opções de crédito diferenciadas para quem tem pressa de crescer. O cartão BNB Agro oferece crédito rotativo com agilidade e comodidade. Já com Planta Nordeste, você tem renovação automática do custeio, além de pré-custeio e comercialização. E para garantir um futuro sustentável, o FNE Sol financia sistemas de geração de energia renovável e redução nos custos de produção. O Banco do Nordeste possui soluções ideais para a atividade rural. Por meio do FNE Irrigação, apoia empreendimentos que desenvolvem a agricultura irrigada, fundamentais para o crescimento da região. E para quem quer manter seu empreendimento sempre atualizado, o banco oferece financiamentos de peças de reposição e manutenção de equipamentos e veículos. No Banco do Nordeste, o futuro é agora. São diversas soluções digitais para simplificar e modernizar sua vida, como cadastro, conta corrente, simuladores de financiamento e login digital. E os pedidos ao fornecedor no cartão BNB Agro são feitos via mobile. É o Banco do Nordeste levando o desenvolvimento digital ao agronegócio. Com o BNB Agro Inovação, o produtor rural aumenta a sua competitividade por meio da incorporação de tecnologias e inovações no seu processo de produção e de gestão, como equipamentos de agricultura de precisão, máquinas autônomas e outros. O Banco do Nordeste tem uma política específica para o agronegócio, destacando-se apoio ao desenvolvimento do cerrado nordestino, incentivo à utilização de tecnologias de convivência com a seca e desertificação, apoio à logística de armazenamento da região, incentivo para ampliação de áreas irrigadas, apoio à pesquisa e à difusão de tecnologias para o agronegócio e estímulo aos projetos de micro e mini geração distribuídas de energia por fontes renováveis. O Banco do Nordeste e a Confederação da Agricultura e Pecuária do Brasil têm parceria voltada para a realização de ações integradas, a fim de ampliar e facilitar o acesso dos produtores ao crédito rural, Como consequência, o acordo deverá proporcionar a melhoria de renda e das condições de vida das famílias rurais atendidas na área de abrangência do banco. O banco mantém ainda parceria com empresas fornecedoras de máquinas, equipamentos e insumos agropecuários para possibilitar a modernização do setor. O Banco do Nordeste atua em estreita parceria com o Ministério da Agricultura, Pecuária e Abastecimento, apoiando os diversos programas do governo federal por meio de sua ação financiadora em consonância com as políticas públicas. É tudo isso e muito mais que faz do Banco do Nordeste o maior parceiro para acelerar o desenvolvimento do agronegócio.
Bom dia a todos, muito bem-vindos, né, a mais uma mesa redonda, tá? Hoje nós iremos falar nessa mesa, né, sobre a eficiência e programação da irrigação. Essa mesa, né, ela é composta por pesquisadores da Europa, tá? Nós temos o Nicola Lamaddalena, né, lá de Bari, na Itália, tá? A Claire Sierra, da França, do Instituto de Irrigação de lá, e também o nosso Bruno Molle, tá? As palestras serão em inglês, pessoal. Então, perfeito, com isso a gente vai iniciar, né? E agora eu vou passar a palavra para os palestrantes, tá? Bruno, everything is okay here. So you can start. Okay, just let me know if you need any assistance.
Okay, good. Well, I wanted to say good afternoon. This is for the European people, but it's good morning for our Brazilian colleague. And welcome to this roundtable. It's quite complicated to organize and to speak in a roundtable where you don't see any of the attendants. Just a number. So I see that there are 19 participants up to now, and it is growing up quite fast. So welcome to everybody. Our presentation or our roundtable is focused on the different aspects of technology and management methods to enhance irrigation efficiency in the context of water shortage or climate changes, or whatever the origin of tension on the resource are. So we have three presentations. The first one is done by Claire Serra-Wittling, which is one of my colleagues from the same team, who will speak about this aspect of irrigation efficiency and water saving. Are we sure that the efficiency is high enough to be able to save water? Then I will myself focus on the aspect related to technology and their consequences on the efficiency of water use. And then Nicola Lamaddalena will present the work which has been done in Bari on the development of a modeling tool to help in managing water on a tactical, which means short-term or more strategical type of approach, which means longer term. So let's talk now. Let's listen now to Claire Serra-Wittling. And the idea is to have the three presentations going on, and to, at the end of these three presentations, to have the questions, as there is a kind of logic in the three presentations that are answering some of the questions that are posed by one speaker, answered by the other. So, Claire, I give you the floor. You have the screen. Go on. And we have 20 minutes.
Thank you. Okay, can you hear me? Can you hear me, Bruno? And the other? Okay,
yes,
thank you.
We can.
Thank you.
Yeah, we can hear. Sorry. Bruno.
Good morning. Good morning, everybody. I'm Claire Serra-Wittling. I'm working with Bruno Molle at the French Research Institute for Agriculture and the Environment. And I'm pleased to talk today about the modernization of irrigation systems to optimize irrigation efficiency and productivity. I will present you some results of a survey conducted in the French context. So first of all, I want to remind you the course of irrigation water in the plot. This is the conceptual framework that will support all of our work. So here you have on this figure the different volumes of water that goes through each step. First, the water is entering the plot, then it is called the applied water, then the water reaching the soil, then the water stored in the root zone, then the water evapotranspired, the water actually transpired by the crop, and at least this water contributes to the yield of the crop. And between each step, you have water losses in the plot. These losses originate from leaks from equipment or from direct evaporation or drift in sprinkler irrigation. These losses can also be the water intercepted by the canopy. The water can be lost by runoff or drainage. Also, the final stock of water in the soil after harvest can be considered as a loss. You have also the weed transpiration and at least the soil evaporation. So we can define the irrigation global efficiency, which is the ratio between the irrigation water actually transpired by the crop and the irrigation water entering the plot. We can also define the irrigation water productivity, which is the ratio between the additional yield resulting from irrigation to the irrigation water entering the plot. We use a modeling approach to assess all these volumes of irrigation water. The crop model is called Optirig. We can model the volumes at each step of irrigation water in the plot so that we can assess the lost volumes that are potential water savings. We can also assess the irrigation global efficiency and the irrigation water productivity as well. The starting point of our study is the following. In the European Union, investments for irrigation modernization are supported by the European Agricultural Fund for Rural Development, and equipment at plot scale is eligible if it allows water savings of a minimum between 5 and 25% of water. And so there was a need in France and in Europe to get references on water savings achieved in different conditions. So that's what we have done. We have collected references on water savings from field trials representative of a wide range of pedoclimatic conditions, crops, and irrigation systems. We collected references over a period of 30 years on 25 different French sites, we covered all types of crops, including corn, other feed crops, fruits, and vegetables. And the aim of the survey was to compare the water consumption of 2 irrigation systems or of 2 scheduling systems. When we compared 2 irrigation systems, we compared a sprinkler irrigation system with a localized system that can be a surface drip or subsurface drip system or a micro sprinkler system. And also we compared for the same system, the water consumption of the system scheduled without soil probes and with the same system scheduled with using soil probes, either tensiometric or capacitive probes. This allowed us to create a database with different data, the year, location, crop, soil type, etc. And here we have the amount of irrigation water applied with the most consuming system, here the sprinkler system, and the least consuming system. It means the localized system. And so we could assess the water saving made by switching from the first to the second system. We could also assess a hydric deficit indicator of the crop season, that is the ratio between the reference evapotranspiration and the precipitation. And at least we wanted to check that there is no yield loss when switching from the sprinkler to the localized system. So the database has in total 93 records of realized water savings. 60 records deal with water saving obtained by switching from sprinkler to localized irrigation, and 23 from water saving achieved by using soil probes. Here you have some examples. You can see, for instance, that when the first system is an overhead irrigation solid system in an apple orchard, and when the second system is an under tree irrigation system with microjets, you can see for apple the observed water savings were between 36 and 52%. For chestnuts, in another experiment, it was 31%. With all this data, we could assess the irrigation water productivity. I remind us that this indicator is the ratio between the additional yield resulting from irrigation to the water applied at plot level. And you can see here that in almost all cases, the irrigation water productivity is higher with the localized system than with the sprinkler system. This is because due to the fact that the localized water system consumes less water than the sprinkler system. Here you have the water savings observed presented as a function of the soil water holding capacity of the soil, and you can see that there is a high influence of the soil water holding capacity, as water savings are more important in soils with a low water holding capacity. Also here between green and red, you have the gradient of the hydric deficit of the year, and for any given water holding capacity, you can see that water savings are always lower in dry years. Here, the water saving observed, so achieved in the fields, are presented as a function of the hydric deficit of the year. And you can see, first of all, that there is a high variability of observed water savings between 0 and 75%. So this means that it is not reasonable to generalize values on water savings observed. And secondly, you can see that there is a great influence of climatic conditions, as water savings are lower in dry years, and they seem even impossible in very dry years on the right of the figure. Now I will speak about the water savings obtained by using soil hydric status probes. You have here some examples. Here, for instance, for a solid set system in a corn crop, you can see that scheduling irrigation with tensiometric probes allowed to realize 20 to 25% water savings compared with the same solid system scheduled without soil probes. Here on the left are presented the water savings obtained as a function of the hydric deficit of the year. And you can see that there is no influence of the climatic conditions on the water saving obtained, contrary to the water saving obtained with, by switching from a sprinkler to a localized system, as I said earlier. On the right, again, the water savings obtained by using soil hydric status probes as a function of the soil water holding capacity of the soil. And you can see also that there is no significant influence of the soil water holding capacity on the water saving obtained, contrary again to the water saving obtained by switching from sprinkler to localized system. And here, just to see that the water savings obtained with capacitive probes or with tensiometric probes are not significantly different. So we wanted to know, where do the realized water savings come from? Here I show you again the graph of the water saving plotted as a function of the hydric deficit of the year. And I have isolated one point of this figure that concern a study case in France on a soil with a low water holding capacity and with a corn crop. And both systems compared are a hose reel machine with a water consumption of 230 millimeter and a subsurface drip system with a water consumption of about 150 millimeter, so that the water saving observed is 34%. Here are compared both yields, and you can see that both yields are equivalent for both irrigation systems. So we used our modeling approach to better understand the origin and the partitioning of water savings. Here you have again both water consumption for the subsurface drip system and the hose reel system. In green, you can see the irrigation water applied that was actually transpired by the crop. This part of water actually transpired is 68% for the subsurface drip irrigation and 49% for the hose reel. So this values represent the irrigation global efficiency that is, of course, higher for the subsurface drip system than for the hose reel system. And the water consumed above this green column represents all the losses at the plot scale. In red, you have the losses obtained by drainage. You can see that these losses are higher with the whole reel system because of the higher amounts of water applied. And the losses by drainage are quite inexistent with the subsurface drip system. You have also in orange the water lost because it remains in the root zone at harvest and will not be used by another crop. This loss is 37% by the hose reel and also more than 30% by the subsurface drip, which underlines that the scheduling of irrigation, also in the case of subsurface drip, could be improved to reduce this final water stock in the soil. And you have two other kinds of losses, the losses by direct evaporation in the air and also transport due to the wind in the air. These losses are only for the hose reel system because they do not exist with the subsurface drip system. And at least the loss by soil evaporation is 14% by the hose reel and doesn't exist for the subsurface drip system. So you can see that there are two types of losses, the types due to the irrigation technology itself, like soil evaporation for sprinkler irrigation and direct evaporation and transport, and other losses that are due to irrigation management. So you can see at the conclusion of this slide that a better global efficiency can be observed for subsurface drip. Water saving with subsurface drip is due to losses reduction, by first changing the irrigation system and second, improving irrigation management. And as I said, water saving could still be enhanced by subsurface drip by improving irrigation management. So in conclusion, water savings realized with localized irrigation system are highly dependent on pedoclimatic conditions. In particular, they decrease when the hydric deficit of the crop season increases. Secondly, water savings realized by scheduling with soil hydric status probes are less influenced by pedoclimatic conditions than the first water savings. And thirdly, water savings originate in reduction of losses, of course. They can be achieved not only by changing irrigation system, but also by improving irrigation management. So, from a climate change perspective, it is important to note that in order to promote water savings, along with investments in water saving equipment, the improvement of irrigators' practices should also be encouraged, in particular irrigation scheduling tools. I thank you very much for your attention.
Okay, thank you, Claire. And thank you for keeping the time schedule. Congratulations, because we are often shifting, all of us. So I will continue myself and try to be well. Alors, I don't see my presentation, so I will try again. Ah, here it is. Here it is. Well, maybe a little bit of introduction. Well, for those who know me, you maybe have seen that the name of our institute has changed. In the beginning of 2020, the former IRSTEA, to which we were belonging, has been absorbed by INRAE, which is a famous research institute on agronomy in France. And for this, at this occasion, INRAE changes his name to add the E to the name, and working on agriculture, food processing, and environment, and not only on agriculture. Well, this doesn't change anything for us in terms of activity. We still have a laboratory, we still have fields to experiment, and we still develop research on the improvement of irrigation efficiency and irrigation performance in general. Well, on my side, I'm more involved in the aspect of technology, and I will try to introduce what issues are to be faced to increase the efficiency of the different aspects of efficiency as they were presented by Claire. If we go back to the sketch that was presented by Claire, the technology is well, the part of efficiency which is depending on technology could be divided in those three categories. The distribution efficiency, the quantity of water which is delivered at the entrance of the field and at the entrance of the block of irrigation, the application efficiency, which relates to the quantity of water that is technically reaching the plant and the soil, and the storage efficiency, which is the quantity of water that is effectively stored in the soil, which is not subjected to drift, evaporation, runoff, or whatever losses that we can have. And those aspects of efficiency will rely on different aspects or different technical aspects. Well, the first aspect, when we speak especially about drip irrigation, is the water quality. The second is climate conditions. The third is hydraulic performance of the system. And the last one is related to soil infiltration and soil storage capacity. So I will try to go through these aspects and give you some highlights of the type of research we are conducting. Regarding the water quality, the concerns are mainly for the use in irrigation of surface water or wastewater, whether it is treated or not. As an information, worldwide, the treated wastewater reuse is representing something, or is concerning something about 36 million of hectares worldwide, which is about 12% of the total irrigated area, and which is a quite surprising figure that was evaluated recently. So the problem that we are related with the use of surface water concerns the loading particles, the presence of algae, the content of solutes, whether they are nutrients when we have wastewater or salts, the presence of pathogens when we are focusing on the dispersion of these pathogens or their regrowth in the system, or the presence of parasites, pollutants, and all these stuff which is escaping the filtration, which is passing through the filtration. They will deposit or grow in the irrigation system, and they may induce drop in the performance of the system. This is concerning especially micro irrigation, of course, with the problems related to clogging, and also can concern sprinkling system, but on the smaller extent than for drip irrigation systems. If we speak about the different form of clogging that are occurring in drip irrigation systems, when we go in the field, because we can work in the lab and we are all very comfortable with the lab, but going in the field is always of interest. If we go in the field and we observe what happens in terms of size of particles when after filtration, we can observe that the particle we find at the beginning of an irrigation systems compared to the particle we find at the end of this irrigation system shows growth in the size of the particle. In fact, inside the irrigation system, we have various types of aggregation phenomenon that occur, and that will result in the case that we have, I am displaying here, and that will result even if the filtration is 80 micron, which is the case in this example. We will end up with particles that could reach more than 500 microns. This is mainly due to the fact that turbulence that happens or that occurs in the distribution system will increase the probability of shocks between particles and the probability of having particles that aggregate together. This is more important when this will be more important when the turbulence of the flow is very high, so consequently at the beginning of the irrigation systems, and then at the end of the system, when the particles that have been aggregated are are sedimenting at the end of the system. Here an example of another example of this problem of clogging, which is related to the presence of nutrient in the irrigation system. Here you have an example of what happens with online drippers that are distributing wastewater in a reuse perspective. We have development of accumulation, diverse accumulation, that will decrease the efficiency of the system and decrease the uniformity of distribution. So regarding this aspect of physical clogging, we have the possibility to analyze the phenomenon which is related to the design of the sprinkler or the dripper itself. And so we have developed in INRAE since 1974 testing methods which is under application at the ISO to evaluate over a duration of 4 weeks the sensitivity of drippers to clogging. The type of results that we have is this one. This is the case for manufacturers. So we have I don't know if you see my mouse on the screen, probably. Excuse me. Oops. I don't know if you see my mouse on the screen. So we have here the discharge that is observed by the different drippers over the 4 weeks. Each week we are adding particles at a rate of 125 ppm and adding progressively these particles from 0 to 80, 80 to 100, and up to 500 microns. At the end of the 4 weeks, we have 0.5 grams per liter of particles inside the water. And we observe the number of drippers that are clogged, and we observe the capacity of the drippers to trap or to let pass the particles. So you have here an example of a dripper with a good manufacturing quality, because all the drippers are behaving in the same manner, except one during the 3rd week that is having problem to digest more or less the particles. And at the end of the test, the drippers are oil clogged, which means that the minimum size of the passage inside the dripper is lower than 200 microns. And so this is used for advising the manufacturers in terms of filtration to select. In this case, for example, we will advise the manufacturer to stay around 100 microns filtration size. The type of particles that we are using are only mineral particle with a phase mix which has to be between these two thresholds and which is constituted of natural soil that is treated like when in agriculture we analyze the soil, which means we remove all the organic matter, we disperse all the particles, and then we have these different individual particles. So you remember the previous sketch. We had a good quality dripper. Here we have another example with a tape. This is a drip tape of rather good quality. It is not a bad one. And you can see that in this case, the heterogeneity of the behavior of the drippers is very, very high. In this case as well, something like 100 micron size particle are not able to pass through 6 over 8 of the drippers. And we have only 2 drippers that are keeping good level of discharge. This is representative of the quality of the manufacturing quality that we had on this dripper, which is not very good, which is very common on drip tapes. Well, I was speaking about first about this aspect of particle. The second aspect, which is driving clogging, is the development of biological or biofin or biological material inside the drippers, which is due to the fact that the water is often nutritive, even if it is in a small quantity. And so we have this development, which is, well, especially important in treated wastewater. We have a development of biofin, which is dependent on different aspects. In this case, we have an example of what we analyzed with treated wastewater again, and with different drippers. We had 3 types of drippers in which we have different velocity, which result in different shear stress. And this shear stress is a way to characterize the flux of the flow of water inside the dripper. And we observe that the higher the shear stress, the higher the quantity of biofin develops, over a period of about 40 to 45 days, which was quite surprising. We were supposing that the biofilm will develop more rapidly in lower discharge or lower velocity, and in fact, with lower velocity, the biofilm is not having enough stuff to heat to grow properly. What is interesting is when we observe this phenomenon of biofilm development, to be able to observe what happens. For this, we have developed an observation system which is using an OCT, optical coherence tomography system that I will describe a little further, and transparent drippers in which we can observe the deposit or the growth of biofilm inside the system over time. In this case, we have three different cases of discharge, resulting in 3 different velocities, and we can observe that the development which may not be very obvious, but we can induce that the development in the 4 liters per hour, the higher shear stress is larger than in the lower discharge. The third type of clogging phenomenon is related to the presence of chemical in solution in the water. In particular, the case of calcium that precipitate in calcium carbonate. This will generally combine with the biofilm, with the development of biofilm. In our case, we were suspecting that the phenomenon of precipitation will enhance the phenomenon of biofilm development, and in fact, it is the opposite. You have here an example of what happens over a period of 42 days with the same dripper that we had before, in which we had wastewater added or not with calcium carbonate. And we can observe that without the calcium carbonate, the biofilm development is much more rapid than without. This is supposed to be due to phenomenon of abrasion that are eroding the biofilm inside the system. Well, I just mixed my slides, and this one was supposed to be to arrive sooner. This is the principle of the functioning of the optical coherence tomography system, which is a non-invasive method that we use with a standard dripper that was put in a transparent tube. What is very interesting is that the resolution is very high, 1.2 micron, and the observation field is quite important as well. And then from using this system, we can observe the development of the biofilm over time and with different layers. So we have what happens at the bottom of the drippers, and then when we go up, we have progressively the development of the different layers that can be observed. And this is used to map the development of the biofilm, and can be used further in simulation of water flow. So this water quality dependent efficiency results from a combination of factors that will result in the development of accumulation of biofilm. This can be controlled, and we have an example of the control that we can get for a combination of particles and biofilm with four different options. The first is a control. The second is just a flushing of the system on a regular basis. The third is chlorination alone, and the fourth is a chlorination plus flushing. So we can observe here that the chlorination, which is not surprising, is very effective. But the idea is to optimize the use of chlorine to reach this cleaning, this efficient cleaning. Then this last slide is just an example of work which is undergoing to develop an optical sensor that will help to identify inside the dripper or inside the dripping system the accumulation of particle or biofilm or whatever to induce this phenomenon and launch the cleaning procedure before. This is an example of the signal that we have between 400 and 2,500 nanometer wavelengths, which is given by different concentration of kaolinite clay. So we identify the different signals that are emitted by different form of clay, different form of biological matter, to analyze with the light that is reflected by the clogging material, to analyze the type of clogging which happens, which will help us define the type of intervention that we can plan, whether it is chlorination, the use of acids, or the use of oxygen peroxide, for example. The second aspect related to efficiency, or I'm sorry, but I don't, well, I'm a little bit late. I see there is a chronometer that I discovered just now, so I'm a little bit late. The second aspect is related to climate. You have an example of what have been measured on big guns in windy conditions. What we observe with as an effect of wind on distribution is, well, a shift of the wetted area, which is not very surprising, and a concentration of this wetted area, which results in an increase on water distribution intensity. Another example is given, again, these are measurements. Another example is given for a solid-state sprinkler, which highlights precisely the loss of uniformity. And if we come back to our example with big guns, you can have, so from the different maps that we had at the beginning, we have calibrated a distribution model that allow us to simulate what happens on a field over a number of climate conditions. And in this case, for example, we have the simulation of the different grid of a plot that represent each of the square or the rectangle that we have here, and on which we can simulate using the OptiRig crop model that Claire was speaking about. We can simulate the quantity of the yield that was product depending on the quantity of water that has been received. This is an example highlighting the effect of the uniformity of distribution on the productivity of each of the plots. Going further about the aspect of climate influence on efficiency, regarding the sprinkling system, the major impact is due to the size of the particle which are produced, and these particles could be evaluated with a special sensor. We are using an infrared sensor that allow to qualify the distribution. This is an example of a sprayer that is used for center pivots, on which we have at a different distance from the emitter the distribution of droplet size in the different distribution of droplet size in volume here, and the distribution of kinetic energy here at the different distance. So these parameters are very important to qualify the sensitivity to wind. We have identified that, and this is the previous one, we have identified using ballistic method that we have two thresholds that are important in terms of size of particle. The first is about 150 or 200 microns. That is representing the threshold for particles to be totally evaporated or totally transported out of the irrigation area. And the second limit is about 450 or to 500 microns, where the drift or the distance to which the droplets will fall from the place where they have been emitted is very, very large. For the other droplets, they are more or less submitted to the gravity. So these droplets are shifting proportionally to the wind velocity, but they are not lost in general. So I will go faster. Well, in terms of climate dependency of efficiency, well, regarding the drip irrigation system, the only effect could be the accelerated precipitation of calcium carbonate. You have an example here. The orifice of the emitter is here and has been totally blocked by the precipitation. This, of course, doesn't occur with SDI. Hydraulic dependent irrigation efficiency, very rapidly. This is a work that has been conducted with our colleague from ESALC, in which we have identified the required sensitivity of monitoring of discharge and pressure to identify as early as possible the decrease in distribution performance of drip irrigation systems. More or less, what we can say is that a measurement of the decrease in pressure, the decrease in pressure related to a 10% to a clogging that is reaching 10% is enough to identify this decrease when it is a little bit more difficult to identify the decrease in discharge. So you have the reference of the paper that is given here if you are interested, because I am too long. To finish the soil aspect related to the infiltration and the storage of the water will be determined by the rainfall application intensity. This is especially the case for center pivots where the discharge or the water application intensity will be proportional to the size of the machine. The longer the machine here is, the higher will be the intensity, and the higher will be the risk of runoff. And we can say that today these parameters are seldom considered in the design of irrigation system, which may be detrimental for the soil. So I will finish my presentation with this one, and sorry for being a little bit late, and I give the floor to Nicola.
Thank you, Bruno. Thank you very much. I will try to share my screen. Where is my presentation? Is this one? Can you see my screen?
Yes, we can.
Okay, perfect. So first of all, good morning to everybody. Thank you, Bruno, and thank you, Claire, for your very interesting presentations. And thank you to all the organizers for inviting me to this very important conference. I've been a couple of times already in Brazil, in Fortaleza, in Inovagri conferences, and it was very, very interesting, but also very nice to meet Brazilian friends and to enjoy with their kind of hospitality. It is quite sad now to be in front of a screen and you know, not to enjoy with Brazilians and international friends over there. But okay, let's hope that this COVID will finish soon and we can go back to the normal life. This is the title of my presentation, which is in line with the previous one. And before starting, I would like to say a few words about the terms water saving, because, you know, there is a lot of talk about this water saving. Somebody saying, okay, but what we lose at the farm level actually is not a loss of water, because such a water can go somewhere else, for example, into the groundwater, and it can be used again by other people, other farmers. Well, we have to take with care this kind of assumptions because, you know, look here in this graphic, we are at the farm level, at the farm scale. So we have the deep percolation here, and the deep percolation are considered losses at the farm scale. But if we go at the basin scale, this is not actually a loss, because it can recharge the groundwater, or it can recharge the root zone of the water. So it is not really fully lost. But in my opinion, we have to be careful. We have to try in any case to have very high efficiency at the farm level, because even if the deep percolation goes to recharge the groundwater, well, to retake water from groundwater, we have to use energy. So we are shifting the problem from the water to the energy. It is true that it is not a loss in terms of basin scale, but it is for sure a loss in terms of energy consumption. So in my opinion, the previous presentations highlighted very much the fact that the irrigation efficiency at the farm level has to be as much as higher as possible. So the work that I'm going to present is related to a study that I did on an irrigation system in Italy some years ago. And you can see in this irrigation district, water was distributed to farmers by a rigid rotational delivery schedule. So water was supplied with a 10-day rotation and with a fixed amount. And if we look at the field capacity and the optimal yield threshold in the farm where I carried out this experiment, we can see that there are moments in which farmers supply more water that is needed. So we have here either runoff or deep percolation, and other cases in which farmers don't have water when they need, but they are forced to have stress in the crop before having water available. Well, with this simulation I'm showing you here, you can see that farmers applied an irrigation volume equal to more than 500 millimeters in the year, in the irrigation season. If farmers would have used water with the on-demand delivery schedule, so if they would have applied water when they really need, when the crop really need such a water, well, they would have not have either runoff or groundwater percolation, neither stress on the crop. So, and in addition, they would have used around 370 millimeters instead of 500. So it means that they could have saved 130 millimeters of water, which is a lot of water. It's 1,300 cubic meters per hectare water saving. And they would have not have, you see, any kind of stress in the crop. So the crop yield in this case would have been much higher. So that's why the important, not only to distribute well the water on the soil, not only the amount of water that we supply to the soil and to the crops, but it is very important and very relevant when do we supply water to the crops. So we have to supply water in the right moment if we want to achieve the best yield and the best crop yield response. In line with that, in the framework of an European project in which Bruno was also a partner, EU Mud for Water project, we have developed a model which is called Safe Irrigation Management Model, in which, in addition to that, we also include the effect of the use of treated wastewater. In fact, this software is composed by 4 different modules. One is the classical soil-water balance. Soil-water balance in which we have, you see, a part of the soil. In this part of the soil, we have inputs. Inputs are irrigation, rain, subsurface flow, and capillary rise. And then we have the outputs, which are the evapotranspiration, the runoff, the subsurface flow, and the deep percolation. And of course, the input and the output have to be equal. Otherwise, we have an additional stock into the root zone of the soil. So this is a classical water balance approach, and we can compute this water balance in terms of root zone depletion or even in terms of soil moisture content. Here you see the 2 equations, which are classical equations. But to this module, we have added also the salt balance model. In fact, starting from a given salt content in the soil, which we called S0, the salt input to the irrigation is the irrigation water, while the salt output is achieved through leaching by drainage water. So accordingly, the mass of salt added by irrigation water, SAI, is calculated as SAI is equal to I, which is the irrigation water that we supply, multiply the electric conductivity of the salted water we are applying to the soil. The salt drained, SD, is calculated as the drainage water multiply the electrical conductivity of the drainage water. Well, therefore, the total salt into the soil can be calculated as the initial content of salt into the soil, plus the salt added by the irrigation, plus the salt occurred by the drainage. Then we have added also the 3rd module, which is the bacteria movement module when we use treated wastewater. This is very important and very relevant. You know, there is a lot of concern about in the world about the use of treated wastewater because farmers are afraid about the bacteria movement by using the treated wastewater. Well, we have added this module and we can compute the accumulation of bacteria, in particular the Escherichia coli, Escherichia coli, in the soil by solving this kind of equation, which is a decreasing exponential law starting from the number of E. coli at a certain time step t, and then looking at how this kind of amount of accumulation of Escherichia coli occurs into the soil by following this equation that is on the screen. And then the fourth module is the nutrients management. In particular, we focused on nitrogen cycle. We focused on the nitrate leaching and uptake, and also on the phosphorus cycle. And let me show you the application of this module, model to a case study which was carried out in Souss in Morocco. Why in Morocco? Well, in Morocco because Moroccan, in particular the IAV, which is the Institut Agronomique Vétérinaire in Agadir, was partner of the project. So we carried out all the experiments in this pilot area in the south of Morocco, very close to Agadir city. Well, we have compared here the traditional farmers' behavior. In this area, farmers irrigate mainly citrus, and they irrigate every day. And you can see here on this screen, on this slide, that this is the amount of water that farmers apply every day to their field, this green histogram, and the gray histogram. And then you have the green line, which is the accumulation of water into the soil. And you see that even when the soil reaches its field capacity, farmers continue to irrigate every day. So we have drainage, this red line. We have drainage into the soil. And you can see that in this area, farmers are used to supply around 1,000 millimeters per irrigation season, 970 millimeters in the irrigation season. If they would use a modeling approach based on the equations that I showed you earlier, you can see that instead of 970 millimeters, they could apply 691 millimeters. So it's is around 300 millimeters less, which corresponds to 3,000 cubic meters per hectare less water. It's really a lot of water, especially in water scarce countries like Morocco. And you can see that we do not have any drainage. Only when there is rainfall we can record some drainage, these red lines, and we do not have any stress and any accumulation of water into the soil. So it is much more performant using the output of the simulation models. In terms of electrical conductivity, you see here there are two lines, one continuous line and one dotted line, when using treated wastewater. Well, of course, when using treated wastewater, if we follow the farmers' rules, we have more accumulation of salt because farmers supply more water, and we have, of course, more accumulation. If we use treated wastewater with the modeling approach, we have less, you see, we have less accumulation of salt because we supply less water, so less salty water. When we use fresh water, we don't have substantial difference between the farmer's behavior and the modeling approach. On the contrary, the leaching fraction should be higher when we use the modeling because we supply less water, so we risk to have more leaching fraction instead of the approach used by farmers. Well, also this slide is very interesting because it refers to the evolution of E. coli, and you can see here that this line corresponds to the accumulation of E. coli when farmers apply their usual delivery schedule. So when they apply water every day. And you see that as they apply more water to the field, of course, there is a higher accumulation of E. coli, while when farmers, if farmers use this modeling approach, they would apply much less E. coli on the soil. So there would be much less accumulation of E. coli on the soil. And in terms of fertilizers, as the treated wastewater is full of nitrate, ammonium nitrates and ammonium phosphates. So you can see that by using treated wastewater, farmers can save a lot of money, because this is the money they have to spend when they use fresh water, and this is the amount they have to spend if they use treated wastewater in terms of ammonium nitrate, in terms of ammonium phosphate. So the farmers, by using treated wastewater, can save a lot of money every year. Well, of course, to apply this modeling approach, the design of modern irrigation system has to be done in the right way. I mean, water should arrive to farmers with the appropriate discharge and with the appropriate pressure. You know, Bruno was showing the effect of pressure head and on the drippers and on the sprinklers. And this is very, very relevant, because if the pressure is not adequate, farmers will not have an adequate way to distribute water on the soil and to the crops. So their yield will be reduced. And also the delivery schedule has to allow the appropriate irrigation time, because if the management agency apply a rigid rotational delivery schedule, even if we have the modeling approach and the modeling tools with us, farmers cannot apply water simply because water is not available, and they have to wait their turn to apply water. So this is very important and very relevant if we want really to save water and if we want really to increase yield production. And of course, capacity development and governance program are very, very relevant, because it is not enough to provide the irrigation agency or the farmer with a good software or with a good technology if somebody does not help them on how to use the new technology in terms of machines, in terms of drippers, and in terms of tools like managers, like the software. And this kind of training is not only for farmers, but I would say that it is rather important to focus this kind of capacity development programs for managers, for designers and extensionists, and at the end to farmers, because all the chain of decision makers involved in irrigation needs to be trained on new technologies and on modeling. And thank you very much. This is all I have to say today. Bruno, the floor is yours.
Okay, thank you. Thank you. Thank you for the interesting and connected presentation, despite we didn't communicate so much before, but we know each other, so it's enough. So I don't know how it works now for the questions.
I have questions here in the presentation. Can you? I can show for everyone. So let me see. I'll share with you the question.
In the meantime, I have a question for Claire. I don't know if I can ask directly to Claire. It's an easy question. How did you compute the yield? Did you use modeling or did you use a questionnaire in your presentation, Claire?
Thank you for your question. We have both data, the observed yield of the farmer, and we have also the simulated yield. And this, we can check that our simulation is good, because the simulated yield is quite the same as the observed yield.
Oh, okay, okay.
The answer?
Yeah, absolutely, yes. So you use both the approach, questionnaires and simulation, and you compare.
Yeah.
Yeah, thank you. Thank you.
Sorry, Bruno, I forgot to translate it. It's the main questions on chat, okay?
Alors, I read the question. It is common in France, both subsurface irrigation drip and hose drill irrigated the same crops. we have just to make a difference between the different type of use of irrigation system, and this is ready for France, but this is also ready for Italy, where we have a large difference between the southern part of Italy and the northern parts, and this is also true for the Central Europe. Most of the real machines with guns are concentrated in semi-humid climate, in places where you have rotations that are mixing irrigated and non-irrigated crops. And the hose reel machines are really the optimal system for moving from one plot to the other. So the subsurface drip irrigation is not very common. It will be, for field crops, for example, it will be present in specific case. I have one example in mind, or two examples in mind. One example is a farmer that for producing corn has a shift from a real machine that was sometimes irrigating the road which is aside. So he shifted from real machine to subsurface drip to avoid endangering the people that are crossing on the roads. This is the first one. And the second one, in places where irrigation is questioned by the population, the farmers shift to subsurface drip or shift to hose the name escaped to me, the hose pipes that we put on the center pivot to put the sprinkler very low, and in places where irrigation is questioned, farmers are trying to irrigate discreetly without showing they are irrigating. So it's well, it's a situation in France. I know that it is specific to France because the other country, the irrigation is not questioned so much. I don't know if I answered the questions.
In fact, Bruno, it is strange. In Italy, I never heard about that people question irrigation. It is new for me. Very, very interesting.
Yeah.
If I can add something, in Italy, we have all the types of irrigation. If we go on the north, we have flood irrigation because we have rice cultivation. We have the Po Valley, where farmers are used to apply a lot of water and for irrigating the rice. And but I have to say that, you know, flood irrigation is not an efficient method to irrigate. But in the case of northern Italy, all the excess of water is going to refill, to recharge the groundwater. If they would use another methods, probably that water from the Po River would have been to the sea. So this is context specific. So in this case, we have actually a groundwater recharge. So what is lost, actually it is not really lost because it is groundwater recharge, but it is only case specific. In the center of Italy, Lazio, Toscana, all these regions, which are crowded of COVID nowadays, we have a sprinkler irrigation. Farmers use a sprinkler irrigation. They prefer to irrigate crops like corn with the sprinkler irrigation. While in the southern Italy where I live, in the Apulia region where I live, most of farmers, let's say 95% of farmers use drip irrigation. It is not so common, even in Italy, to use subsurface irrigation because of the problem of clogging of the drippers, and after certain time you have to renew the pipes. But some people are starting to use subsurface irrigation, especially when water is really very, very scarce. And as you show with subsurface irrigation, you don't have any kind of evaporation, and you don't have any kind of drip deep percolation. So it is very useful. The only problem is that is the technology. I know that there is some manufacturer who have developed some new technologies trying to reduce the effect of clogging in subsurface drippers, but still it has to be, developed more.
So it means that the clogging in the subsurface drip is higher than the surface drip. Is that okay?
Well, you cannot control mainly. I don't know if it is higher or it is equal, but when you have a dripper, you can substitute it. You see and you substitute. When you have subsurface, you don't see it. And then, so you don't know what happened there.
Thank you.
Yeah, so
maybe.
Okay,
yeah,
sorry.
I think Claire will continue because on the same matter.
I just wanted to complete the answer of Nicola and Bruno. In France, there are also special cases where subsurface drip irrigation is used. For instance, when the shape of the plot is not totally suited to the shape of the center pivots, the farmer can use subsurface drip irrigation to complete the pivot irrigation. For instance, if so the surface, the area irrigated by the pivot is a circle, of course, and the plot is not a circle. So the part that is not irrigated with the pivots can be irrigated with subsurface irrigation. It's another example of the use of this specific system. But anyway, in France, this system, subsurface drip irrigation, is not used on very large areas. But it is used sometimes for experiments, so to study how to use this system, how long it will last in the time, how it has to be used, the flushing that Bruno explained, the treatment with the chlorine and so on. It's more experimental as commonly used.
Yeah, I could add that on our experimental field in Montpellier, we have 9 plots which are subsurface drip irrigated, and that we use to compare to other technology. And what we can say is that on the average, the water saving between properly managed sprinkling system and subsurface drip, the water saving is between 0 and 20%. 0 is for the case when you have specific conditions, specific humid conditions, for example, during the year, and 20% is when you have very dry conditions, when you have windy conditions and so on, and so you are saving. But what is more interesting is that we have identified a saving of about 30% of the nitrogen quantity, which is another very interesting benefit. But anyway, this system is very interesting, very promising, but is very expensive and very sensitive, and so you have to get highly skilled farmers to manage it, and this is one of the main problem that we can get. So it's a good idea, but complicated to manage. Alors, question, could you explain a bit how did you determine effective rainfall? You mean,
I can answer this question.
Maybe, yeah.
Yes, I think the question is for Claire.
Yeah.
Sorry.
The effective rainfall is the rainfall that reaches the soil but that is not lost through runoff and drainage. So it means the rainfall that effectively remains in the root zone.
So, but the question is, how do you determine? You just estimate?
Yes, so in our model, runoff is not taken into account, only drainage. So we calculate the effective rainfall as the rainfall reaching the soil minus the rainfall that is drained.
Okay, great.
Sometimes FAO has recommended some models to compute the effective rainfall, and some other authors just suggest to take 90% of the rainfall, and that's it. So 90% of the rainfall is considered as effective rainfall. It depends, of course, on the intensity of the rainfall. It depends on the type of soil. It depends on a number of conditions. But usually, these are the way to compute the effective rainfall.
That's great.
Yeah, there is a comment on the contamination of drip irrigation systems. Just a few words on this, and one of the results that I was presenting is a work where, in addition to the development of biofilm in the system, we have also identified the type of bacteria that develop inside the system. And we have evidenced that the E. coli that Nicola was speaking about are not feeling very comfortable in drip irrigation systems. That means that the competition with other pathogens make them uncomfortable, and they cannot develop in this system, which is not the case for Enterococcus, for example. Enterococcus bacteria are able to withstand the specific condition of drip irrigation systems, and so the consequence is that we have suggested to the French government to review its regulation to follow more than E. coli, the Enterococcus in the water. So just a comment on this. Well, I don't have any comparison between well yet, because I know that that our colleagues from Unicampi and ESALC are working on it. I don't have any comparison in the different type of contamination that we have in drip irrigation systems. But of course, we have twinned a number of experiments between ESALC, Unicampi, and our facilities, and we reach the same type of results, whatever the side of the Atlantic is. So, which is well, we are happy with it, which is not always the case with this type of comparable results. And of course, Brazilian farmer could use recommendations. Yeah, of course. And regarding the collaboration with Brazilian researchers, so well, the history began with Silvio, well, which is the manager of this interesting conference since the beginning. And we have continued mainly with ESALC and Antonio Pires de Camargo. And while we were moving to Unicampi, we are continuing with them. This is for the activities related to irrigation technology. And we have also another collaboration which is developing with the University of Florianopolis, which is more focused on wastewater reuse, and the University of Vitoria, which is related to more overall approaches of management of water and effluent in urban area, with recycling of gray water, urine as a fertilizer, and organic matter from coming from food and after compostage. So it's well, we are focusing on the water management aspect and the use by plants of nutrients and water, but the overall study is more general.
So these are for me. Congratulations, that's nice. Thank you very much. Can you comment about the adoption of salt irrigation models by farmers, extension companies, decision in Italy or other countries? Okay, well, I can comment because especially in my region has only one river. I live in the Apulia region, which is on the south of Italy. And we have only one river on the north of this region. And it is overexploited. And so water is absolutely not enough for irrigation. And on all the rest of the region, farmers are used to take water from groundwater. And you know that when you take water from groundwater, there is no control. This is really a very, very important problem in most of the countries in the world, the control of groundwater, the groundwater management. And in Italy, in the southern Italy, it is exactly the same. So farmers take water from groundwater, and there is a lot of sea intrusion into the groundwater. So farmers irrigate with salty water. But and that's very complicated because there is no control. We have water users organizations which are in charge to control irrigation. But they only control the irrigation with distribution systems, so what we call collective irrigation systems. They do not control the groundwater. The only thing that has been imposed by the Italian government is that farmers have to install the flow meter on the well. Otherwise, they do not get the authorization to drill the well. And in fact, farmers have installed the flow meter on the well, but nobody controls it, because you can imagine, only in my region, in the Apulia region, there are 230,000 wells legally. So we don't know how many illegal wells there are. So who can control 200,000 wells on the territory of my region? So nobody can control. So what happens is that farmers use salty water, but there is no control on that. And the farmers only recognize that they are doing mistakes when they see the crop yield response, which is reduced because of salt water. And also the structure of the soil is damaged because they use salty water. And then fortunately, we have some rainfall, which is not too much, which is around 600 millimeters per year, but with a quite good intensity to lithiate part of the soil. So we don't have very big accumulation, but there is, being short, there is no control on that. So farmers use salty water, but nobody controls that. And the farmers only recognize that they are doing mistakes when the mistakes already occurred. So there is an early warning system. I have developed some years ago a prototype of a device which can be installed on the well, and farmers can use electronic cards to activate or deactivate the well. And there is a sensor inside of this device in which the salt is monitored. And when there is a certain threshold of this salt into the water, there is a red line that highlight, and farmers can recognize that they are starting to make mistakes. But this is only a prototype I have in my lab. I'm joking, and I'm used to call this prototype as an invention, as my invention that nobody knows. because you know, nobody wants to control the groundwater. Farmers don't want to be controlled because they want to take all the water that they have, and managers don't want to be, you know, to have an extra load of work, because controlling, you know, so many wells is a lot of work for the managers. And policymakers don't want this control, because otherwise they will lose votes from farmers and votes from the managers. So, you know, even if the the invention is ready and it is in my lab, it is only to show to friends that comes to my institute and to see the facilities that we have in the institute. But in fact, I didn't succeed to convince any farmers, any managers, and any decision makers, any policy makers in my region. So that's a pity, but what to do? And then can you talk about how much wastewater used in irrigation in Italy? Well, that's very easy answer. We don't use wastewater, only at the level of experimental fields, because the legislation in Italy is so heavy that even if we treat a lot of water, we use tertiary level treatment and so on, nobody wants to take the responsibilities, because if there is an infection, nobody wants to take the responsibility of infection. So at the moment, I have to say, maybe it is used in an illegal way. So if there is water, if there is, you know, the treated wastewater going into a canal before going to the sea to be discharged into the sea after the treatment, of course, and farmers don't have fresh water, they use such a treated wastewater. But you know, nobody knows that. In fact, personally, in summer, I prefer not to eat raw salad, for example, because I know that sometimes use treated wastewater, non-treated wastewater, and I don't trust that. So I prefer to eat fresh salad only when I am at home, when my wife is washing it properly. But if I go to a restaurant, I prefer to avoid because of that. But legally, I mean, officially, let's say, very few farmers use treated wastewater, only at experimental level, not actually at the level of, you know, as a strategy for Italy, because of these very heavy constraints.
And from France, can you, Claire or Bruno, can you have
France,
talk about?
well, there are only 3 or 4 countries in Europe that have legislation for treated wastewater reuse. Italy, Spain, Portugal, and France, as far as I know. And we have a very different level of restriction in the different countries. I think that Italy has the most restrictive regulation. Just to give an example, there is an obligation to verify something like 50 micropollutants in the water to be able to reuse it, when for the potable water, the number of parameters of micropollutant is about 37 or something like this, which is very surprising. And well, recently the European Union has created its own regulation, which is less restrictive than the Italian one, but more restrictive than the French one. Just to give you an example, when you want to irrigate vegetables, the limit in terms of E. coli that you can use is less than the quantity of E. coli which is allowed for qualifying water as bathing water. So this is very surprising. Yeah, so it's about, so you are allowed to have 10 E. coli per millimeter for irrigating vegetables, but you are allowed to declare your water as bathing quality when it has 100. So, well, this is just to speak about regulation, which is a complicated stuff, and well, I don't want to argue about it and so on. in terms of quantity, we estimate that the quantity of water, of wastewater which is reused in France is something like 0.5 to 1%. It has been estimated around the Mediterranean, and it is something like 2.5%. And as was saying Nicola, and as I was saying before, the treated wastewater reuse can be direct or indirect. If you reuse directly, you have a very restringent regulation. If you reuse it indirectly, then you don't have any regulation. So what happens, especially in Italy, I remember the discussion with people from the Po Valley. They said, well, there is a nice treatment plant in Milan that is achieving a very high level quality water, which is able to achieve this quality of water. And in fact, they just use it at 20% of its capacity, and the other water is going back to the canal or to the river, and then it is pumped by the farmer further. And that was what I was saying when I was saying that there is about 36 million hectares that receive wastewater every year. In these 36 million, about 6 million only are controlled wastewater. And the others are indirect reuse related to the discharge of the treatment plant in the rivers in which the farmers are pumping. This is coming from a study that was made by geographers. The first writer is Thebo, T-H-E-B-O, which identified all the water that is pumped downstream from the cities of more than 500,000 inhabitants all over the world. And so, of course, it is an estimation. So in this estimation, he comes to the conclusion that about 30 million are uncontrolled treated wastewater reuse, when 6 million are controlled.
Yeah. Just Bruno, to complete what you said about the Po River, farmers are allowed to use the Po River water to irrigate their field, and the concentration of E. coli in the Po River is 100,000 E. coli per milliliter, and they cannot use the water coming from the treated wastewater, which maybe is, I don't know, 10 E. coli or 100 E. coli per milliliter, and they are not allowed to use it because of the restriction of the law. This is really very, very, very sad, let's say. Okay.
This for all the speakers now.
Here there is a question on magnetic treatment. I don't know, some years ago, I remember that my institute got a project on the use of magnetic water, but I was not in charge for this project, so I don't know the results. If Eusimio Fraga send me an email, I can try to forward the email to some of my colleagues who work specifically in this project. Maybe they can be more exhaustive for Eusimio. Sorry, I don't have any output of the project.
We were contacted recently by some people that are selling this kind of equipment, and well, with Claire, we were ready to do something, but when we proposed this to the team, that was more complicated because there were some doubts about the consistency of this system. Well, I am skeptic, but I really would like to have answers to some of the questions that I have. Well, it seems that experimentally, our colleagues from INRAE in Tunisia, that you know, Nicola, have been evaluating these systems, and they have identified some progress in the water use efficiency. But when you have a look to the significance of the results, it can be questioned. So it seems that there are some progress, but it's quite complicated to identify the exact progress. I don't know what you can say, Claire, about that, because we were discussing about it together.
We know that this company is now carrying on a project on these magnetic treatments for pivots, for center pivots. So maybe in 2 or 3 years, we will have some interesting results about this.
Oh, that's good. So you are using the center pivots, yeah, because in Brazil it's common to some people start using drip irrigation.
So until now, this company was selling its magnetic solution only for vegetables, so quite small volumes of treated water. But on center pivot, the technology is a little bit different because the volumes to be treated are far higher, and they wanted to test their technology on pivot for this purpose.
Yeah, they have examples, and there is 1 or 2 publications also on the effect of this technology on the development of biofin. The development is significantly less with this technology than without. So there is something happens, certainly, but today we cannot know, we cannot say what it is exactly, and yeah, and well, they speak about water saving. They speak about 20% or something like this. And as far as I remember, the CIT made an experiment on this, and they identify something like 3 to 5% water saving, which is more or less the uncertainty of the measurement. So in terms of water saving, I'm not sure that we will gain a lot. They speak about better efficiency of nutrient uptake, maybe. They speak about biofilm development restriction. I would believe this because the biofilm development is very erratic and very there is a lot of parameters that intervene on it, and so maybe, and well, who
knows?
we have more questions than answers on this technology.
They speak also about a better water retention in the soil due to the interactions of water and pores of the soil, but all these points have to be further investigated.
Yeah, the significance of this should be really tested. At the moment, there are more questions than answers. I agree with with Bruno. With Claire. Yeah. Okay. Okay, I think that the session is closed. Am I right?
Yes, yes. We don't have any question anymore. So, Bruno, if you guys have to give the last word, that's okay. Actually, we have around 100 people watching this round table, because we have people inside of this room, and you have a platform that's and much of the guys are watching the platform.
Okay, good.
Okay.
And
okay. very proud.
So Bruno, you can say a few words to close the session.
A few words to close the session. Well, it was nice to meet some of you. We are in a virtual situation since quite a long time, and it's kind of complicated. I hope that that we will be able to meet again together as soon as possible. As I was saying, the work with Brazil is continuing, and well, the different papers has been published. Other are under publication, and as Inovagri is focusing on Fortaleza, we have a work which is undergoing with Fortaleza. The work I was speaking about the integrated approach of gray water, urine, and organic matter management in cities. A case study will be developed on Fortaleza, and this is a kind of sub-product of what we have presented with Claire, and approaching integrated questions related to water and nutrients and so on. Well, that's, I don't know if you have something to add, Claire and Nicola. You can sub-conclude.
Let me just give an input to the Brazilian friends. Is that in the past, my institute was focusing all the activities in the Mediterranean countries. So for me, it was quite hard to open to other collaborations in other countries rather than the Mediterranean basin. Nowadays, the administration board decided to open the collaboration of my institution, of the CIHEAM, not only Bari Institute. We have 4 institutes in Europe. And so now I'm allowed, and it would be much easier for me to work in cooperation programs even with Brazil. So if you see that there is any possibility to collaborate together, it will be a pleasure. I mean, my institute now is open to this kind of collaboration, even outside 2 Mediterranean countries. So maybe we can start new collaborations with Brazilian friends.
It's a great news. Thank you.
Claire, maybe you can conclude about the perspective in soil conservation agriculture that may interest a lot Brazilian people, because as it is highly practiced in this country.
Yeah. Yes, I know that Brazilian people have been working for a long time on the subject of conservation agriculture. And we are now starting also the conservation agriculture practice on our experimental platform in Montpellier, in south of France. And we would like to study the influence of the conservation agriculture on the soil properties in relation to the water, the hydric behavior of the soil. And we would like also to look for the adaptation of irrigation practices to agriculture conservation. The question is, in the Mediterranean context, is it possible to save water through the conservation agriculture or not? We want to answer this question. And also we would like to study the use of the subsurface drip irrigation under conservation agriculture conditions, because as there is no till in this type of practice, we think that subsurface drip irrigation could be adapted to this kind of agriculture. So we will also explore this technology aspect with subsurface drip irrigation. So we are very open to any collaboration with our Brazilian colleagues on this topic.
Thank you all. We are very pleasure to have you here and for you accept this invitation to participate of this virtual event. We hope that next year we can do in Brazil, and you guys can visit us again. It will be great to have you here. That's okay?
Thank you.
So
thank you very much.
Thank you. See you later.
Bye-bye. Bye-bye, Bruno. Bye-bye, Claire. Bye-bye, Alexandra. And
Bye.
Bye.
Thank you for the invitation.
Thank you.